Hello, I'm Brandon Skaggs from Cypress Semiconductor, an Infineon Technologies company, and on behalf of my co-authors Chris Turman and Joe Whitehouse, I'm here to present Hierarchical UPF Design, the Easy Way. For our agenda today, I'll spend a few minutes reviewing the motivation for this paper and what we hope to contribute to the conversation. Next, I'll present a simple hierarchical UPF design where parameterizable IP are reused, which will take us into a conversation of some common hierarchical UPF design reuse issues that our design and verification teams commonly encounter. Next, I'll discuss our findings when attempting various hierarchical UPF design methods, including the level of support for each we found within our EDA toolchain. Finally, I'll present an analysis of the results and give some concluding remarks. Our motivation is that time to market is king. Designing, and more importantly verifying, designs hierarchically allows reuse of these efforts and reduces the time it takes to produce a product for the market. Reuse in RTL is easy. We have clear definitions of naming scope, port maps, system Verilog interfaces, parameters, a rich language meant to allow hierarchical design. In spite of improvements in UPF LRM revisions, a combination of LRM gaps and EDA vendor LRM support makes reuse of IP power intent at higher levels of design less straightforward. We found that options are not supported evenly across tool vendors, and some options don't do what you might expect. An understanding of these issues can inform best IP design practices and possibly suggest improvements in future IEEE 1801 revisions. To that end, the goal of this paper is to present a case study of hierarchical UPF design with highly parameterized power-aware IP, including the specific language constructs attempted and the issues encountered. To reach this goal, this presentation will present a simple hierarchical design using pre-verified configurable IP, allowing us to discuss common issues related to reusing IP power intent at system level. We'll present experimental findings, and then finally, we'll conclude with a list of recommendations we think would be helpful in making hierarchical UPF design easier. Let's begin by examining a simple hierarchical UPF design. Let's define an IP-A as an IP with two domains. P-top is relatively always on compared to the rest of the IP. However, the IP also contains an internal domain, P-retention, that can be switched off, with key state elements retained with a defined retention strategy. Additionally, the power state table defines an optional state where a lower voltage can be provided for the retention supply. Know, however, that if IP-A's P-retention supplies are connected to always-on supplies at system level, IP states off and retention for P retention would be unused and retention cells would be unneeded. Also for our system, let's define another IP-B with top-level domain PMUX, which is relatively always on compared to its other domains. But since IP-B could have its inputs driven from IP that are switched off, it contains isolation strategies for protecting downstream logic. Note that the context of IP-B's instantiation will decide if any of the defined ISO strategies are needed. So let's now describe our system. Our top-level domain PSYS is always on, but the retention logic does not make use of the low voltage option for retention cells. A second switch domain, P-switched, contains logic switched off to conserve power, including an instance C1 of IP-A. A second instance of IP-A, C2, lives in the top-level always-on domain. IP-B instance C3 has inputs from both C1 and C2. Note that in this system configuration, the retention strategy of C2 and the isolation strategy in C3 for the inputs from C2 are both unneeded. Now that we've seen a sample hierarchical UPF design, let's discuss the issues that often arise when this methodology is used. One concept that needs to be understood and addressed is the scoping of IP content. The load UPF command allows loading of IP power intent at a specific hierarchy, allowing any objects referenced relative to IP scope to resolve. However, this means each IP instance contains uniquely scoped names for any domains, supply sets, etc. that are defined, even if the definitions are the same. In our example, PD top in instance C1 is unique and independent with respect to PD top in C2. There is no set equivalence command within UPF language to automatically set these uniquely scoped items as equivalent. Some EDA tools do provide such functionality, but these methods are tool specific at best. However, UPF does provide the concept of a composite domain in UPF 2.1 for gathering or clubbing domains into groups. So perhaps this is a solution to our issue. We'll look into this later. Supply set abstraction is another issue to consider in hierarchical UPF design. UPF does provide the concept of supply sets for grouping supply nets for handling into something akin to system Verilog interfaces. And commands exist in the UPF LRM for operating on these supply sets, for assigning supply sets to domain handles, setting sets as equivalent during power state analysis, and even for connecting macro PG pin type pins to supply set functions. The command connect supply sets seems like an obvious choice here for connecting system supply sets to IP supply sets. Looks easy enough? Well, we'll look at this in a moment. As we saw in our example system, we need to be able to describe strategies in ways that allow the strategies to apply only when they're needed. Reusable IP can be instantiated in ways that render defined strategies unnecessary. Isolation strategies can be written to only be active when they're needed, with options like diff supply only, for example, or with the simple concept that strategies don't apply where no boundary exists. However, there's no option for retention strategies to allow them to be disabled if the logic is never turned off. We could pseudo-parameterize the UPF, although in Tickle this would be with if-else clauses with Tickle variables. And in fact, both the UPF2 and UPF3 LRMs provide methods for passing parameters to IP intent as Tickle variables. This seems like it'll be easy. Now that we've discussed the theoretical concerns, let's look at what our design teams actually found when attempting to apply this methodology. Now that we've discussed the theoretical concerns, let's look at what our design teams actually found when attempting to apply this methodology. First, a few comments about our philosophy and approach to this study. An existing mature design that was already in production was used. The top-down database was cloned and modified to use this bottom-up hierarchical approach. The more abstract methods available in the language were first attempted. We then would revert to more explicit language only when issues with the approach were found. We looked at results from simulation, static multi-voltage rule checking, synthesis, and layout compared to the existing flat methodology results. We preferred the production versions of all EDA tools in order to maintain fidelity with the production database that we were comparing with. Here notes are added where newer versions of a tool improve support from the versions we originally used. And finally, Any not applicable entries in the results represent cases where the method or command was not attempted due to known issues with the rest of the tool chain. This was simply a practical limitation of where our design teams could spend time on this effort. Recall our first concern was with IP-scoped objects. Would composite domains help us manage this? Not really. The command has no real support within our implementation toolchain. Furthermore, it seems it was not ever really intended for use with implementation tools. Even the LRM describes that it doesn't represent a physical region like other power domain definitions. The impact to our teams is that they had to manually handle each IP scope domain. Maintenance with this approach is tedious. Any new IP required updating of our flow scripts. We believe the UPF LRM should provide a better mechanism for setting equivalence between domains created by scoping. Now let's look at supply set abstraction. How easy is it to make associations or connections between our IP-defined supply sets and system supply sets? As you can see from this chart, it's not very easy at all. Support for these supply set commands was abysmal with the tool versions that we used. For associate supply set, Simulator A originally only supported associations that were from top to IP, but a later bug fix in a newer version allowed this to be fully supported. Synthesis Tool B only allowed primary domain supply sets to be assigned, not auxiliary supply sets. For our physical implementation tool D, this was actually not supported in any way, shape, or form. Connect supply set, well, Simulator A says in their documentation that they supported it, but based on the fact that it wasn't supported in the rest of the chain, we never actually tried it. And then finally, Synthesis Tool B does claim to support this command, but only for supply nets and not supply sets. So what was the bottom line? Well, we had to revert to making explicit supply net to port connections. We would ask that our EDO vendor community support these supply set commands so that our design teams won't have to explicitly make connections for each supply within the design. Now let's see how we fared with optional strategies, specifically retention strategies. Recall in our case how C2 has a retention strategy that's unneeded. Synthesis results shown that just the presence of the strategy was enough for retention cells to be instantiated. Having a power state table that indicated the domain would never be switched off made no difference. We ultimately handled this by having teams provide separate UPF files for retention strategies, which we'd load only where needed. In this example, we're only loading the retention strategy for C1, which is switched off. We believe the UPF LRM should be enhanced to include an if necessary option for retention strategies. Another option for handling optional strategies would be to include some tickle variable if-else clause that would enable the strategy when appropriate. And recall we have some UPF commands like load UPF protected in UPF2 or the enhanced load UPF command in UPF3 to handle this safely and automatically. Easy, right? How does the saying go? If a UPF command falls in the forest and no EDA vendor is there to implement it, does it still make a sound? As you can see, neither the deprecated UPF 2.1 command or the improved UPF 3 command were supported enough across the toolchain to make this a viable approach. Well, you may be saying we could instead manually handle the tickle variables ourselves, but this can also be risky. All tickle variables in the IP intent would need safely defined default values for all implementation conditions, which are difficult to know ahead of time. This also creates the possibility of namespace collisions. You see, any tickle variables in the presumably frozen pre-verified IP would share a namespace with the sourcing top-level UPF. Newly defined variables at the top level could have unintended impact on unrelated portions of the design if the names collide. These collisions could be difficult to identify ahead of time. Let's have a raise of hands. Has anyone here ever had issues with the multi-file compilation units in System Verilog? It's that idea. A definition in one place could have unintended consequences elsewhere. So we believe EDA vendors should support the existing UPF language constructs that provide a mechanism for passing parameters to an instanced, loaded UPF in a namespace safe way. Finally, let's look at the issues related to reusing IP power states at system level. Experimentally, we found it difficult to manage IP whose states were unused. In this case, C2's often retention states that appear in the IP UPF file but are really not ever activated at system level. Formal tools complained whenever unused IP states were encountered. In other cases, conflicts between IP and system power states caused both to be dropped, and we found this later when we missed some crossings during analysis. We actually had the vendor recommend disabling IP states via a tool-specific option to prevent this from happening. So we believe the UPF LRM should provide better mechanisms for handling scoped power state conflicts. So now let's look at a summary of our results. Firstly, care must be taken to maintain lists of IP scope domains for use in synthesis and PNR scripting. Direct net-to-port supply connections are really the only reliable way we found to make connections across UPF scope. Here, this is just simply a statement that the supply set connections just weren't useful. Optional IP retention strategies should be maintained in independent UPF files to make them easier to apply only where they're needed. And then finally, IP and system power state definition conflicts can be difficult to resolve. Defining the system power states from top down can avoid this. Now let's wrap things up with our final analysis and conclusions. The UPF LRM should provide a mechanism for explicitly setting domain equivalence between parent and submodule domain definitions. We shouldn't be forced to rely on vendor-specific commands. UPF constructs that operate on supply nets should be supported by EDA vendors in a manner that allows connectivity, not just equivalence for power state table analysis. The UPF LRM should include an if necessary option to retention strategies to allow optional retention strategies within a switch supply. If the power state analysis can show that an isolation is not needed because some domain is not off relative to another, then it ought to be able to infer whether retention strategies are needed as well. EDA vendors must support UPF language constructs that provide a mechanism for parameterized intent definitions that avoid namespace conflicts. In this case, the Language Reference Manual Committee did their job and provided the commands. We need the EDA vendors to step up and allow us to use those. Next, the UPF LRM should provide more flexibility when defining power state tables to enable IP to specify which states can be dropped or overridden at integration level and which should be considered essential. Additionally, the LRM should define clear rules for defining hierarchical states and how conflicts should be handled. And now our conclusions. Design complexity and time to market requirements continually push for more efficient leveraging of design and verification of subcomponents, and practical hierarchical low-power design methodologies are critical for accomplishing this. However, while the components of this methodology are in place, limited support by EDA vendors for the more contemporary LRM concepts, as well as some, albeit minor, inconsistencies in the LRM itself, stand in the way. As we approach the 10th anniversary of the LRM revision that provided the constructs and methodology to make it possible, this paper identifies that the practical hierarchical reuse of power intent, while possible, is a long way from being easy. Well, that's all we have. Thanks for your attention. We'll open the floor for questions, but feel free to find me after the session if you want to continue the discussion over a beverage of your choice. I welcome suggestions as to what we've gotten wrong in our analysis. Thanks.